Okay, so we spent some time talking about properties of solids and liquids and gases, and now we're going to look at what happens when those solids and liquids and gases change into another state of matter. So the first thing we want to look at here is just some simple vocabulary that we use to state when something changes from a solid to a liquid to a gas, or in between all three of these. Now, some of these words you're going to be very familiar with. Obviously, you know that when a solid changes to a liquid, we call that melting. And when a liquid changes back to a solid, we call it freezing. Hopefully those aren't shocking to you. When a liquid turns into a gas, we call that vaporization. We say it vaporizes. And when a gas turns into a liquid, we call that condensation. So obviously you know lots of examples of a solid melting into a liquid, or liquid freezing, liquids vaporizing. You know, we use dew as an example. When water vapor condenses into a liquid in the summertime, and the water vapor in the air condenses into dew on the grass or your car. A lot of times, maybe when you're taking a shower and the mirror fogs up in the bathroom because of the condensation of the water vapor. Now, two words you may not be as familiar with are sublimation and deposition. Both of these explain situations where a substance is converting between a solid and a gas. When a solid turns directly into a gas, we call that sublimation. We say it sublimes. Carbon dioxide is a good example of this. Solid carbon dioxide is what we call dry ice, and that sublimes directly into a gas. It doesn't go through a liquid phase. Snow does this a lot of times in the winter. We'll get a snowfall, and even though it'll be below freezing, the snow seems to disappear over a period of time. And that's because the air is usually so dry when it's cold out that the solid sublimes. It turns into water vapor in the air. When a gas turns directly into a solid, we call that deposition. We say it deposes. Frost is an example of deposition. In the winter, you go out to your car and you're running late for school, and if it's been a cold night, you have to scrape the frost off your car first. Well, that's because the water vapor in the air has deposed on the surface. Because it's below freezing, it's gone from being a gas to a solid. In the summertime, that gas condenses into a liquid because it's above freezing. So make sure you're familiar with each one of these vocabulary terms. Now, you might also notice that some of these arrows are green and some of them are blue. The blue arrows represent an endothermic change. That means this action needed to absorb energy in order to happen. So when a solid melts into a liquid, it has to absorb heat, absorb energy. Think of an ice cube sitting out on your kitchen counter or in a glass, and it has to absorb heat from the surrounding air in order to melt. Just like a liquid has to absorb heat to turn into a gas, to vaporize. That's why a lot of times we heat up water on the stove, and it's absorbing that heat to vaporize. The green arrows represent an exothermic change, meaning they release energy. So when a gas converts into a liquid, when it condenses, it's giving off heat. Or when a liquid freezes, it's releasing heat. And so each one of these changes involves an energy change that needs to be accounted for. And we'll talk a little bit about that energy change later on in this chapter. In the lab last week, you measured the heating curve of water. And so I wanted to review that quickly here as it pertains to a phase change. Now, you noticed a couple things, hopefully, that when you started out here with ice in the lab, the temperature stayed constant until all the ice melted. And then once the ice was melted and you had all liquid water, that's when you saw an increase in temperature, only after all the ice was melted at this point. And then it increased in temperature up to the boiling point. And then once we reached the boiling point, that temperature remained constant. Now, here's why. When a substance is in one phase, and this is representing ice down here. solid water. When a substance is in one phase as a solid, if we're adding heat, we are increasing the kinetic energy of the particles, meaning the particles are moving faster. And remember that temperature is a measure of the average kinetic energy. So as we're adding energy down here, the temperature is increasing because we're increasing the kinetic energy until we get up to the melting point. And then all of a sudden at the melting point, the temperature stays constant, which means our kinetic energy is staying constant. That's because at the melting point, we're rearranging the molecules. The molecules are in a nice orderly position here as when they're in a solid. But then when they start converting into a liquid, we got to pull them apart. They got to rearrange themselves. And the energy of position is called potential energy. And so whenever we are at a change of state, a melting point, a boiling point, freezing point, we are changing the potential energy. We're increasing the potential energy, and the kinetic energy is staying constant. Whenever we have a positive slope, we're increasing the kinetic energy, i.e. the temperature, and the potential energy is staying positive. So at the melting point, we're rearranging those atoms. All that heat energy is going into breaking the intermolecular forces, pulling those molecules apart. Then once they're all pulled apart and in the liquid phase, then we can start increasing the kinetic energy. Then they use that heat energy to move faster, and that increases the temperature until we get up to the boiling point. And then at the boiling point, again, we're rearranging those molecules from a liquid into a gas. And so we're increasing the potential energy. And then once it's all steam or water vapor, we can increase the potential or the kinetic energy again. So anytime you see the temperature increasing on the graph, that's an increase in kinetic energy. Anytime you have a plateau on the graph, we're changing the potential energy. So temperature change is a change in kinetic energy. And kinetic energy is energy of motion. So you relate that to molecular motion. And anytime during a phase change, during the melting or the boiling point, we're changing the potential energy. We're changing the arrangement of the molecules. And that temperature is going to remain constant. So if you're cooking something at home, it doesn't matter if the water's been boiling for 30 seconds or if it's been boiling for 30 minutes. You're not getting hotter water. The water's staying the same temperature as long as it's boiling. And here's another look at that phase or the heating curve as they appear in the phases. If we're not looking at the energies, but we're looking at exactly what they are, ice, water, or steam, we see that here. And you can compare that to the other graph that we just looked at in terms of their energies. So always remember that the temperature remains constant during a phase change. When we talk about evaporation, and I know you're familiar with evaporation, but evaporation occurs at the surface of a liquid. Whenever you have a mud puddle outside after it's rained, it's the molecules on the surface of the mud puddle that are evaporating, that are gaining energy from the surrounding atmosphere, from the sun, from the pavement, from the ground, just the air temperature. They're gaining energy, and they are converting from a liquid to a gas. They're vaporizing. And they have to gain enough energy to overcome their intermolecular forces. Remember, intermolecular forces are the forces that are holding molecules together. Another word that you want to be familiar with is volatility. And volatility measures the evaporating rate. Things that are volatile evaporate quickly. Things that are not volatile evaporate more slowly. An example of something that is volatile is rubbing alcohol. And you know, rubbing alcohol has a distinct odor to it. And a lot of times, maybe before you get a shot or a vaccination, they'll put rubbing alcohol on your skin as kind of a sterilizing technique. And it evaporates quickly because it's very volatile. Gasoline is very volatile. Basically, anything with an odor, something like that, or fingernail polish remover, we say is volatile because it's evaporating quickly. Water is not very volatile. Water has a very low volatility. Water takes forever to evaporate. The way to get it to evaporate quicker is to heat it up. And that's why we say it depends on the temperature and the intermolecular forces. We're going to talk about a concept called equilibrium when we talk about phase changes there. And equilibrium is when you have two opposite things occurring at the same rate. And let's look down here at the picture. This will give you some example. So we have a beaker filled with water. Put a lid over it. As soon as you put the water in there, there are water molecules on the surface that are evaporating. And here we got them evaporating. We see them right here. Eventually, the water level goes down because some of the water molecules have evaporated. But we're going to reach a point where the number of water molecules evaporating match the number of water molecules that are condensing. Because if we have all water vapor up here or more water vapor, they're going to say, hey, let's condense and become a liquid again. So they're going to reach an equilibrium where we have as many water molecules evaporating as we do condensing. That's what equilibrium is. If you think of a basketball game, basketball team has 5 players on the floor. If 3 players come off, 3 players go back on the floor. If 1 player comes off, 1 player goes back on the floor. You can have different numbers of players subbing, but you're always going to have 5 players on the floor. It maintains an equilibrium. And that's what we're doing when we talk about molecules that are condensing and vaporizing at the same time. As long as they're doing it at the same rate, it's called an equilibrium. Now, vapor pressure is a measure of that vapor. And if we look over here, let me go back a slide, this is vapor up here. So the pressure that it exerts is called vapor pressure. And it's the pressure of a vapor above a liquid at equilibrium. And it depends on the temperature and intermolecular forces. What we mean by that, the higher the temperature, the more vapor pressure you're going to have. If you think of a boiling pot of water on the stove, as you heat it up, you increase the water vapor, which increases the pressure. And if you leave a lid on a boiling pot, that lid starts to rattle and shake because we've increased the vapor pressure. And we've done that by increasing the temperature. And then the intermolecular forces, the lower the intermolecular forces, the higher the vapor pressure. Rubbing alcohol is a very low intermolecular force, so those molecules can spread apart from one another, and that's why it has an odor. And if we'll note this over here, this graph, this is a vapor pressure graph. It's on page 378 of your textbook. As we increase the temperature, the vapor pressure of the water and the diethyl ether both increase.